Hi, this video will take you through the next set of notes, Module 7, Probability Continued or Probability Formulas. So this video introduces the idea of adding different compound events to get probabilities together for compound events and multiplying probabilities together for sequential events. Okay. So when two events are mutually exclusive, then we can figure out the probability of each event by adding the results together. In a Venn diagram, that means that if we have two outcomes A and B that don't intersect at all, right? They're mutually exclusive, no overlap. Then we can calculate the probability by adding them together. This is pretty intuitive. So calculating the probability that A or B occurs, again, is through addition. So if we wanted to figure out what the probability is that a person has type A or type B blood based on data that we have, right, then we look at the probability that they have type A blood and add to that the probability that they have type B blood. In this situation, we know the probability that a person has type A blood is 0.42, and the probability that they have type B blood is 0.09, meaning that the probability that they have type A or B blood is a probability of 0.5100. Okay, simple enough rule. Okay, the next rule is for when we have repeated trials. We want to know the probability that one event occurs and then the next event occurs, and the first event has no effect on the other. Then we can calculate that probability by multiplying our probabilities together. Okay, here it's really important that our probabilities are written in decimal form. If they're in percent form and you multiply them together, the value is not going to work out for you. So let's look at an example. So we've got 4 potential donors, and we're using the CBS, the Canadian Blood Services data, again from the previous example. We want to figure out that all 4 are type O. So that would be the probability for out of 4 are type O. So that'd be the probability that the first is type O, which is 0.46. The probability the second is type O, 0.46 again. The third is type O, and then the fourth is type O. So we end up having whatever the probability is of 0.46 to the power 4. Putting that into our calculator, that comes out to 0.0448. Okay, if we want to know what the probability is that all 4 are type A, then the calculation is quite similar. Since P type A is 0.42, then the probability that all 4 are type A is 0.42 to the power of 4, or 0.0311. Amazing. Okay, when we don't have the same outcome repeated multiple times, so it can be good to have a way to keep track of our work. So we'll reintroduce the tree diagrams. So consider you have a bag that has red chips and blue chips in it, or tokens, if you'd rather call it that, and we're going to select 2 chips out and replace after each turn. We want to figure out what the probability is of selecting 2 blue chips. The 2 blue chips. So using our tree diagram, we know we could get a red chip or a blue chip after the first term, and then a red chip or a blue chip again. Okay. What will change on our tree diagram this time is we'll put the probabilities of going down each path. So the probability of getting a red chip the first time is 7 out of 12. The probability of getting a blue token is 5 out of 12. If I want to figure out the probability of getting a second blue chip, then that would be 5 over 12 again. The probability of selecting 2 blue tokens is 5 out of 12 times 5 out of 12, which comes out to a value of 0.1736. Okay, this idea of organizing in a tree diagram is useful as well if the probabilities do change on us as we go through an experiment. Same idea, we've got 7 red chips in our bag and 5 blue chips. We select 2 chips, but we do not replace after each choice. We want to figure out the probability of 2 blue chips in this scenario. So again, I can select a red chip or a blue chip. My probability of selecting the red chip is 7 out of 12 to begin with, and my probability of getting a blue chip is 5 out of 12 to begin with. After my first choice, though, again, I get a red chip or a blue chip. My probability changes. My probability of getting a second blue chip is now only 4 out of 11. The total number of chips left in the bag has changed, and the total number of blue chips have changed. So my probability of selecting 2 blue chips without replacement would be given by the product of 5 12ths and 4 11ths. Okay, in this scenario, our probability drops to 0.1515, or about a 15% chance. Okay. On the last page, we introduced the idea of calculating donors when they're both the same. So if we have 2 potential donors, we want to figure out the probability that they're both type A. Again, we could draw a tree diagram. We know that there are 4 times 4, 16 possible outcomes, and only one outcome has both being type A, right? The probability of both type A, the probability that the first person is type A is 0.42. The probability the second is type A is 0.42 again. So our total probability that they're both type A is 0.1764. And now our next question is a little bit different because we want to figure out the probability that at least one is type A, or type B rather. This is a more interesting or complicated problem because we know there are more than one way to have at least one person being type B. We could have the first being type A and then the second being type B. We could have the first being type B and then the second being anything. We could have the first being AB and then the second being B, the first being O and then the second being B. So there are several different paths we have to consider, and so that complicates our probability calculation here. We could figure out how many different paths there are and add all of those together, or we could use our idea of a complement again. The complement of at least one is none. So if we can calculate the probability that none of them are type B, then the probability that at least one is type B would be 1 minus the probability that none is type B. So the probability that none or neither is type B, well, we'd have to, again, think about that as a complement. So we know aside the probability that somebody has type B blood is given by a percent chance of 9, so a probability of 0.09. So the probability of not B is 0.91. So the probability that neither is type B would be 0.91 times 0.91. Plugging this into our calculator, we get an outcome of 0.1719. Okay, that way, if we can think about using complements, is a bit quicker than adding up the probability down each of those, in this case, 7 different paths. Okay. So the next page has some practice for you. I'd say in the first one, actually let's do the first one together because I think it's easier to actually do this using paths. We have a scenario where we know 9% of men have a type of color blindness that prevents them from distinguishing between red, green. We've got 3 men selected at random. I want to find the probability that 2 of them will have the red, green color blindness. So if we think about our tree diagram, at each choice, it could be yes or no whether they have red, green color blindness. We know there's a 9% chance that they do, and so a 91% chance that they don't. Okay, we could think about our tree again, and each choice, those probabilities continue. Because we have 2 options repeated 3 times, we have a total of 2 times 2 times 2, 8 possible outcomes. Of those outcomes, we're trying to figure out how many of them have the result that we're interested. How many of them have 2 of the selected individuals having red-green color blindness. So it could be that the first 2 we select do, and then the third one does not. That's one possible path. We could have that the first one does, the second one doesn't, and the third one does. Or we could have that the first person doesn't, and then the next 2 have the color blindness. In each of those scenarios, along each branch, we see a probability of yes repeated twice and no appearing once. So along each branch, we have the probability of 0.009371 appearing. And this time we're going to take that multiplication rule and then we're going to combine it with the addition rule. We have to add that probability along each of the branches. So we're going to take the probability and add it to itself 3 times, or to take into account all 3 branches. 3 times 0.007371 comes out to 0.0221. Okay. So consider the next 2 practice questions. Pause the video, try them out, try and draw your tree diagram and label it, and calculate using the product rule and the addition rule if necessary, what the resulting probabilities will be. Okay. For the first one, we have a coin flipped and a die rolled. There's only one successful outcome to consider, and so we can just multiply the 2 probabilities together. The probability of flipping a head is 1 out of 2. The probability of rolling a 4 is 1 out of 6. Putting those into our calculator, we get a probability of 0.0833. In the next example, depending on the scenario, we either have 1 or 2 paths to consider. When selecting 2 blue balls, there's only one way to do that. It would be to select a blue ball both times. So we just use our multiplication rule. The probability of the first blue ball is 2 out of 10. The probability of the second blue ball is 2 out of 10. Multiplying those together, we get a probability of 0.0400. In example B and C, when we select a blue ball and a white ball, or a red ball and blue ball, there's 2 different ways that we could go down those paths. We could select a blue ball first and then a white ball second, or a white ball first and a blue ball second. Similarly, we could do our red ball first and a blue ball second, or blue ball first and red ball second. Because of that, we multiply the probabilities by 2 to take into account the 2 different paths. Okay. If you have questions, please stop by WebEx office hours and ask, and I can explain it more in depth. Otherwise, try out the homework problems and then work on the activity sheet. Okay. Talk soon. Bye.